Okay, just going to go through a request from exercise 10F on page 176, question 2. We've got two particles P and Q, masses Km and 3m respectively, where K is less than 3. In other words, that is lighter than this one. The particles are connected by a light, inextensible string which passes over a smooth, fixed pulley. The system is held at rest with a string taut, the hanging parts of the string vertical, and with P and Q at the same height above the horizontal plane. The system is released from rest. After release, Q descends with acceleration 1/3 g. So 1/3 g meters per second squared, and that would go up with 1/3 g meters per second squared. Calculate the tension in the string as Q descends. Okay, so you want to resolve one of these. So lots of unknowns for P. Has got Km. This one's got 3m. So I think we resolve Q only. Okay, what forces are acting on Q? Well, it has a weight, 3 mg. It's attached to a string, so there's a tension, T newtons, and that's it. And it's accelerating. So F equals ma, Newton's second law. The mass of this object is 3m. The acceleration of this object is 1/3 g. Forces going with the motion, 3 mg. Subtract the forces going against the motion, which is t. And we have to make t the subject. So 3 times 1/3 disappears, so that's just mg. So t would be equal to, add that to the other side, subtract that, you'd get 2 mg. So the tension is 2 mg newtons. You can leave the g in there, or you can write g as 9.8 and get 19.6 m. Doesn't matter. Newtons. Okay, part B wants you to show that K is equal to 1.5. So this time we're going to resolve the other particle. Label the forces acting on P. So it has a weight, which is kmg. It has a tension because it's attached to a string, and that'll be the same as this one, T newtons, and that's it. And this particle is accelerating as well. So F equals ma. The mass of this object is km. Acceleration in this object is 1/3 g. Forces going with the motion is t. Forces going against the motion is kmg. Substitute our value of tension in, which is either of these. I'm going to use the 2 mg one. 2 mg subtract kmg equals, simplify this, k over 3 mg. And lots of things simplify. There's an m common to everything, cancel out the m's. There's a g common to everything, cancel out the g's, and you're left with 2 subtract k equals k over 3, or 2 is equal to, add k, 4/3 k, to give you k is equal to, times by 3 divided by 4, which is 1.5, as required. Okay, state how you've used the information that the pulley is smooth. So if the pulley is smooth, we've got no friction between the string and the pulley, which means The tension is constant, and also we've got the acceleration for both particles will be exactly the same because the friction is negligible. Right. Part D, we've got some more information. So after descending for 1.8 seconds, the particle Q reaches the plane. It is immediately brought to rest by the impact with the plane. The initial distance between P and the pulley is such that in the subsequent motion, P does not reach the pulley. Show the greatest height in meters reached by P above the plane is 1.26 g. So what's going to happen is Q is going to fall, hit the ground, and it's going to move a specific distance. P is going to move up that distance, but also P, once Q has hit the floor, it's going to have a velocity, so it's going to still move up a little bit, but just under its own weight. So you've got two distances to work out. Firstly, how far Q drops, and then how far P goes up after Q has dropped. So part C. Okay, so let's do that on Q. S is the thing you want to work out. U is the thing that you told us at rest, system's at rest, I believe. Let's just double check that. Yeah, release from rest. Velocity is unknown. Acceleration they gave to you is a third g. And the time taken for it to hit the ground is 1.8. So we want something again. S, U, A, and T. So S equals UT plus a half AT squared, which is equal to 0, 1.8 plus a half, a third G's times 1.8 squared. I'm going to leave my answer in terms of G, so 0.5, half times the third G, but I'm not going to write the G in because I want to give my answer in terms of G, times 1.8 squared is 27 over 50, or if you prefer 0.54 G. That's in meters. Now, as I said, go back to the diagram. Q drops 0.5 G meters. P goes up 0.54 G meters. But at the top, P is going to have a velocity, and that velocity is going to be the same as what Q's was when it hit the ground. So I'm going to work at the velocity of Q as well. So this time you want to work out final velocity, so V equals U plus AT, which is equal to 0 plus a third G times 1.8, and that would be 0.6 G meters per second. So the speed of Q as it hits the ground is 0.6 G meters per second. The speed of P once Q hits the ground is 0.6 G meters per second. But then once Q hits the ground, the string becomes slack, and the only force acting on the object is its weight, which means its acceleration will be 9.8 or minus 9.8. So let's pursue that. S is unknown. Its initial velocity is 0.6 g. Final velocity at its greatest height would be 0. It's going against gravity, negative 9.8, decelerating. Time is unknown. So we have v squared equals u squared plus 2as. S is equal to 0 squared, subtract 0.6g squared over 2 times minus g, and this is equal to 0.6 squared is 0.36 g squared on the top minus 2g, which simplifies to 0.18 g. So that's the extra distance it moves. So the total distance would be that plus that. So 0.54 g plus 0.18 g, which is equal to what's that equal to? 0.72 g. So that's how far P is moved. So P went up by 0.54, then it went up a little bit more, which was 0.18 g. But the question is, show that the greatest height above the plane. So you actually want to add in the extra 0.54, how far away they were at the start. So there's an extra extra 0.54 on top, 0.54 g, to give you not 0.72 but 1.26 as required.